Chapter 2: Trauma, Instinct, and the Brain. The Fight, Flight, Freeze Response. When I was a kid, on the farm, I woke up one morning to a weird sound, almost like a baby crying. I went outside, and in the yard was an opossum, lying there, crying and gasping for breath. He had a broken bottle around his neck that was choking him. He must have gotten it stuck around his neck when he was young, and as he grew it eventually began to choke him. So I got a towel and wrapped him in it so he wouldn't bite me, and he went limp and unconscious. I cracked the bottleneck with a hammer, unwrapped him, and he just lay there for a few minutes. Then he began to shake all over on the ground, and after about a minute got up and staggered off. The story was told to me by a patient who had been injured in an auto accident and who had experienced a similar physical event, the discharge of a freeze response that he had observed in the opossum as a child. The neurophysiology of trauma. A number of theories concerning the biological response of the body to acute and chronic stress have developed over the past century. They have clarified the intricate and interrelated responses of the brain, the autonomic and hormonal system, the behavior involved in stress and trauma. Cannon presented the concept of the sympathetic adrenal stress response, linking the role of the adrenal medulla and epinephrine to the body's adaptation to emergencies. Celia introduced the theory of a general adaptation syndrome, GAS, in response to prolonged stress, characterized by three phases: alarm, resistance, and exhaustion. His concept addressed not only the acute fight-flight response, but also the sustained self-protective effort of the body in the face of ongoing stress. The following text presents a simplified and abbreviated review of how the brain and body respond to such a life threat. The brain's pathways for the acute response to a threat are primarily located in the right half of the brain. They receive messages primarily from the sensory organs located in the head related to sight, smell, taste, hearing, and vestibular sense, balance. This process of sensory scanning of the environment is called the orienting response, a physical act of side-to-side head movement that brings all of the sensory organs of the head and neck into play. These messages are then sent to the thalamus, a relay center in the middle of the brain. This sensory information is then routed by the thalamus to appropriate areas of the cerebral cortex that involve perceiving sensation and initiating movement. It is also sent by the thalamus to the limbic system, the emotional brain, particularly the amygdala, the nucleus or center for arousal. The amygdala is the brain's alarm system and storehouse of emotion-linked memory. It basically evaluates the emotional content of the sensory messages, particularly whether they represent danger. Input from the sensory organs of the head and neck are also sent to the locus ceruleus, a cluster of cells in the reptilian brain stem that is the most primitive early warning system of the brain for arousal. The locus ceruleus also sends messages directly to the right amygdala through the neurotransmitter norepinephrine, and this input ups the ante for that arousal. Olfaction, sense of smell, accesses the amygdala directly without traversing the filter of the thalamus, suggesting the role of smell as the primary message system of survival in many mammals. The amygdala then sends information to the right hippocampus, the brain nucleus center for processing conscious memory, where a cognitive and conscious structure for the threat-based information is first formed. The hippocampus, along with other limbic structures, also plays a role in modulating the threat response. Every brain nucleus is balanced by other modulating brain centers, a system of checks and balances routinely fine-tuning the brain's responses. The hippocampus then sends this revised information to the right orbitofrontal cortex, the OFC, for the purpose of further information and memory processing, and for further modulation of the amygdala. The OFC evaluates the threat for its severity, and either ramps up or tones down any further survival behavior through its influence of the amygdala. If the threat is meaningful, the OFC organizes physical motor defensive behavior, fight or flight, as well as autonomic and hormonal responses to this threat. Another limbic system center, the anterior cingulate, also plays a role in modulating and regulating the signals sent throughout the limbic system by the amygdala. In concord with the OFC, the cingulate gyrus inhibits the amygdala if the threat is perceived as being relatively minor. As we'll see, the cingulate also shares with the OFC a role in facilitating maternal-infant and societal bonding. Centered in the hypothalamus, the brain center for regulating the autonomic and endocrine systems, are also activated by the OFC. One role of the autonomic nervous system ANS is regulating the unconscious systems of energy storage and expenditure. In the face of danger, it stimulates pathways the sympathetic fight-flight nervous system, leading to the release of epinephrine or adrenaline by the adrenal medulla. The specific systemic effects of epinephrine include mobilizing glucose from glycogen in the liver, constricting blood vessels in skin and abdominal organs, dilating blood vessels in skeletal muscles, and increasing pulse, blood pressure, and cardiac output. All of these effects allow the brain, muscles, and heart to operate efficiently in fight or flight. The hypothalamus also stimulates the hypothalamic pituitary adrenal HPA axis, the brain pathway for hormonal control. Hormones of the body's endocrine system are important contributors to managing threat and stress. Release of corticotrophic releasing hormone (CRH) by the hypothalamus triggers release of adrenal corticotrophic hormone (ACTH) by the pituitary. ACTH in turn facilitates release of cortisol by the adrenal cortex of the two adrenal glands sitting astride each kidney. Cortisol, well known as the stress hormone, actually acts to prepare the body for prolonged, sustained threat. It promotes retaining sodium by the body, which results in increased blood volume, and also mobilizes serum lipids and increases blood sugar for energy use. Cortisol also inhibits ongoing brain arousal effects of norepinephrine and selectively inhibits the HPA axis, another of the body's balancing servosystems. So, although it seems a little counterintuitive, cortisol also acts as a brake on the brain's arousal mechanisms. Later effects of cortisol promote sustained cardiovascular stability in the face of ongoing stress and prevent circulatory collapse. It does all of these things at the expense of short-term sacrifice of energy storage and diffuse tissue injury, or catabolism. The diseases of stress described by Selye, including diabetes, hypertension, arteriosclerosis, and stomach ulcers, have been attributed to exposure to abnormal amounts of cortisol under prolonged stress. Some researchers also feel that the more slowly acting cortisol effect may act to promote avoidance conditioning in response to ongoing stress. Brain responses to stress. The immediate effects of the arousal neurotransmitter norepinephrine on the brain include increased alertness and focus, immediate enhancement of short-term memory, dilated pupils, increased muscle tone, and divergence outward movement of the eyes to expand the field of view. The immediate effects of body-based epinephrine and brain-based norepinephrine prepare the organism for the high-level neuromuscular activity required for ensuring survival in the face of threat. The fight-flight response. These effects promote short-term preparation of the brain for intense alertness, and the neuromuscular and cardiovascular systems for high-level, short-term skeletal muscle and cardiac activity and energy expenditure. Activation of the fight-flight response, of course, may be triggered by excitement as well as by threat. The basic physiological sympathetic nervous system response of the prey in response to threat is mirrored by that of the predator as it prepares for attack. Pre-game jitter. Stage fright, sexual arousal, and the thrill of the roller coaster ride all reflect the physical sensations associated with arousal in the face of threat. What separates the experience of the fight-flight response from that of anticipatory excitement, of course, is the meaning of the event to the participant. This piece of information processing takes place in the hippocampus, comparison of new information with past associative memories, and the orbitofrontal cortex, problem solving and planning. Whether the animal or human then assumes the role of predator or prey based on this higher level cognitive process, the end result of epinephrine-based arousal is similar. The initiation of intense muscular activity and exertion. Excitatory neurotransmitters and hormones fuel both the attack of the predator and the flight of the prey, initiating a high-level energy expenditure response in both creatures. Many species operate both as prey and predator in the pecking order of eating and being eaten throughout the animal kingdom, and mobilize epinephrine at both ends of the spectrum. Adrenaline in an equal opportunity energizer, and whether the weasel is catching the mouse or being caught by a hawk, the initial physiological effects of both predation and flight are similar in many respects and contribute to the function of resisting, escaping, or attacking. Very soon, however, the meaning of the arousal sequence assumes an important role in subsequent events involving the brain and hormonal systems. Mason has introduced the role of physiological meaning into the stress response equation, disputing Celia's avoidance of cognitive mediation of the stress response. Under Mason's concepts, a more complex interpretation of cortical hypothalamic pituitary circuitry is involved in the stress or fight response and allows for a broader range of behavioral response to threat or arousal. Mason maintains that the neurological and hormonal events of predation and defense diverge and lead to quite different behavioral and physiological responses. Other brain neurotransmitter systems also contribute to the effectiveness of the fight-flight response. Other brain neurotransmitter systems also contribute to the effectiveness of fight-flight response. Norepinephrine, as we have noted, facilitates alerting mechanisms and transmission of messages throughout the brain's central sympathetic pathways. Endorphins, the brain's pain-modulating neurotransmitters, are also released, accounting for the well-documented increased pain threshold in acute arousal. The obvious function served by endorphins includes blunting of pain reflexes and inhibition of conscious and unconscious self-protective responses that might interfere with effective survival behavior. For example, with the aid of the analgesic effects of endorphins released with fight-flight arousal, the injured soldier is able to complete the physical activity necessary for his survival without the interference of debilitating pain. The wounded prey animal is able to continue its fight-flight behavior without instinctively tending to its wounds. Release of endorphins as part of arousal also has interesting implications concerning brain reward mechanisms in human behavior. Since arousal related to predation or excitement is also linked to endorphin release, it is easy to appreciate the reward involved in high-risk recreational activities associated with the adrenaline rush. Because this experience also involves the pleasurable reward of endorphins. Risk-taking thrills seem unique to the human species, and it is clear that certain personality traits may predispose to this kind of behavior. Some evidence suggests that this trait may be apparent in childhood. At any rate, one does not see weasels jumping into the talons of hawks just to experience the thrill of the wild ride. Once again, the meaning of the event that triggers the relatively stereotyped initial neurological and chemical contributions to the fight-flight response likely has a marked effect on later similar behavior. Animals and humans cycle in and out of varying states of arousal many times a day in response to thousands of widely varying stimuli. This cycle takes place between the ergotropic or energy-spending activity of the sympathetic nervous system and the trophotropic or energy-storing activity of the parasympathetic nervous system. The main effects of activation of the parasympathetic nervous system mediated by the neurotransmitter acetylcholine include slowing of the heart, lowering the blood pressure, shunting of blood away from the muscles and to the abdominal viscera, activation of the digestive process and storage of nutrients. It is also the state in which the acquisition of information through declarative memory with the storage of facts and events best take place. However, high levels of norepinephrine may interfere with certain types of memory storage, resulting in declarative memory associated with high arousal being permanent, but often inaccurate. Although the parasympathetic nervous system is relatively inactivated in arousal, it does play a role in the freeze or immobility response, the third and least understood or appreciated part of the fight-flight-freeze sequence. The animal model. Those of us fascinated by animal behavior in the wild love to watch shows on TV devoted to observations of animals in this setting. Many of the TV specials relate to the prey-predator experience and sometimes display this in graphic and even grisly detail, at least to our civilized eye. If one closely watches the details of pursuit of the prey by the predator, one will see that the fleeing prey may sometimes collapse and become limp, even before being seized by the predator. An example is a film involving a gazelle pursued and run to the ground by the cheetah. At the moment that the cheetah caught the gazelle, it struck the gazelle lightly on the flank, at which point the gazelle collapsed and lay inert on the ground in the freeze or immobility response. In another example, after fighting off a pride of lions for more than half an hour, the lone water buffalo was knocked off its feet, at which point it became limp, immobile, and frozen. In other words, when fleeing and fighting are no longer physically possible, and the prey animal is in a state of helplessness, it will frequently enter the freeze or immobility state, a totally instinctual and unconscious reflex. This reflexive behavior is common in most species, including insects, reptiles, birds, and mammals. Since most such reflexes have evolved as a means of perpetuating the species, the freeze response clearly is of critical importance for survival. In a surprising number of cases, the attack of the predator may be triggered by the instinctual response to movement of the prey rather than by hunger. In such a case, the freeze response of the prey may abort the attack of the predator and result in survival of the prey. The freeze response mimics death, sometimes fooling the predator enough to leave the scene of its kill and gather its offspring without delivering the tooth and claw coup de grace, thereby allowing the prey to recover and escape, as in playing possum. In addition, the freeze response, which is analogous to the state of dissociation in humans, is associated with additional release of endorphins, rendering the animal relatively analgesic. Another purpose of freeze analgesia may be to inhibit self-ministering activities such as wound licking, which could impede escape of the prey animal in the case of arousal from the freeze. The basic laboratory model of the freeze response utilizes the method of inescapable shock. Although acute inescapable shock in the previously unexposed animal initially induces a state of acute arousal and defensive postures, subsequent inescapable shock produces a consistent freeze in the face of threat, resulting in manifest or learned helplessness. Inescapable shock. Yes, the animal will quickly discover the means of escape through trial and error, and may never experience a freeze. By definition, that option does not exist in inescapable shock, where trial and error escape techniques are to no avail. In the face of continued shock, threat, in the face of helplessness, the animal will eventually freeze. Animals who have experienced IS with freezing sufficiently in the past will continue to exhibit passive immobility and continued freeze in the face of repetitive IS, even if presented with a new possibility of escape. They seem to have lost their ability to problem solve and learn, not to mention to fight or flee, having faced shock in the past without means to escape. Perpetuations or frequent experiencing of the freeze response clearly creates a learned tendency to freeze in the face of even minor threat. In addition, animals exposed to several episodes of IS linked in time with neutral stimuli will begin to exhibit freezing in the face of the neutral conditioned stimuli presented independently. A freeze response triggered by a traumatic event may become linked to ambient environmental cues through conditioning, just as Pavlov's dog learned to salivate to the sound of a bell if it were paired with food. So, environmental cues, although intrinsically benign, may similarly serve as traumatic stimuli if they occurred at the time of a traumatic experience. Finally, attempts to break through freezing from IS by administering shock as a punishing stimulus result in relative increase in freeze behavior rather than triggering escape behavior. These findings therefore suggest that repetitive exposure to IS seems to impair basic storage of memory and information. IS conditions the freeze response to benign but trauma-related cues and assures that freezing will eventually follow trauma even if escape is feasible. Comparison of these animal behaviors has led Van der Kolk and colleagues to postulate that IS may be a biological model for PTSD. Such observations have also led Nijenhuis, van der Linden, and Spinhoven to draw a parallel between animal defensive traits that are triggered by severe life threat, such as freezing, and the characteristics of dissociative assumption of the immobility response is associated with a dramatic change in the state of autonomic equilibrium, along with the release of endorphins. An animal in a state of high sympathetic tone, fighting or fleeing for a period of time at the onset of the freeze theoretically may have an autonomic nervous system in a state of having both accelerator and the brake on simultaneously during the freeze. However, I believe that it is more likely that rapid and exaggerated sympathetic-parasympathetic oscillation characterizes the freeze. As you will see, this unstable autonomic state may predispose the trauma victim to many of the diseases of trauma involving the viscera, the organs of the chest and abdomen, the digestive and circulatory systems. With onset of the freeze, the racing heart will slow to a crawl, blood pressure will drop, and tense muscles become flaccid. The bowel and bladder sphincters may relax, resulting in involuntary defecation and urination. These effects are produced by the dramatic influence of the dorsal vagal nucleus, a brain center in the reptilian hindbrain or medulla. The dorsal vagal nucleus regulates the functions of the viscera, the organs of the chest and abdominal cavities, including the heart and the blood vessels of the body. It essentially is the engine of the parasympathetic nervous system and enforces the body's responses not only in resting and digesting, but also in freezing. In the state of the freeze, the focused and alert mind becomes numb and dissociated, at least in part due to high levels of endorphins. Memory access and storage are impaired, and amnesia may be expected for at least some of the events occurring during the freeze. The frozen animal or person is in a state of suspended animation, with high levels of parasympathetic activity and endorphins, with variable residual of the preceding state of high sympathetic arousal. This state represents a distinct departure from the usual homeostatic equilibrium between sympathetic and parasympathetic systems. In mammals, the freeze response is indeed a perilous and unstable state. The freeze discharge. In the most cases, the frozen prey animal does not need to deal with the relatively unhealthy state of the freeze response. It becomes another animal's meal. High levels of epinephrine and endorphins apparently do not affect taste. In some cases, however, the frozen prey animal survives the period of immobility without being killed. Subsequent events in this case are of critical importance to the thesis of this book. In virtually all such instances, at some point, the animal will arouse and begin to tremble. This may be as imperceptible as a shudder, or as dramatic as a grand mal seizure. In such cases, analyzed by slow-motion video, the trembling will resemble the last act of the animal before freezing, the act of running. The animal's behavior in what Levine has called the freeze discharge seems to resemble an unconscious attempt to complete the act of survival, as if the last protective motor or muscular activity is locked in unconscious procedural memory and needs to be released or completed, perhaps as a means of discharging retained autonomic energy. This motor and autonomic response may persist for several minutes and is usually terminated by a series of deep sighing breaths, a means of re-regulating autonomic homeostasis. The animal at this point will usually arouse fully, regain its feet, often stagger a bit, shake itself, and then run off, apparently non-diverse for its life-threatening experience. Long-term observations of such animals do not seem to show any harmful effects on behavior, health, or other measures of survival. It would appear from these observations that animals in the wild possibly possess an instinctual means of dissipating autonomic activity stored and accumulated in the freeze response. Figuratively speaking, they seem to instinctually complete the act of escape within their unconscious memory through the freeze discharge. By this means, I feel that the discharge effectively extinguishes all of the unconscious procedural memories of what the body tried to do to escape the life-threatening event, so that these body memories are relegated to past experience and don't return to haunt them or induce another freeze whenever they experience cues to that event. This remarkable phenomenon may occur in a much more subtle fashion, and may take place many times a day in the life of a prey animal. The gazelle may arouse to the scent of predators on many occasions, manifesting an alerting response with tensing of muscles, and with scanning movements of the head and eyes, an instinctual behavior called to orienting response common to all species. If they perceive that the threat is false, they usually then return to their calm grazing state, but usually only after a slight muscular shudder or trembling. The bird that inadvertently flies into a window and is stunned will often remain immobile when picked up by the concerned homeowner and cradled in the hand. When placed on the ground, it will frequently arouse, shake, or tremble, and then fly away, having effectively discharged the stored autonomic energy of its freeze, and extinguished its arousing procedural sensorimotor memories. A patient told me a story about saving a caged pet rabbit from a burning house. The rabbit appeared limp, unresponsive, and supposedly dead when found by the homeowner. Suddenly the rabbit went into convulsions, after which it aroused and then appeared to be normal. What the patient interpreted as an episode of smoke inhalation in a rabbit was clearly a freeze response, with a healthy and life-affirming discharge of retained autonomic energy. This stereotyped neuromuscular reflex response in fact may have represented completion of the truncated act of flight within those parts of the brain that process and store conditioned survival-based memory. The human anomaly. Very little literature addresses the freeze response in the human species, even in the case of overwhelming threat and trauma. It is rare for a human being to actually collapse and appear unconscious without physical injury. Although some people will be shaky and tremulous after a shocking event, they seldom pursue the relatively stereotypical and involuntary physical behavior of the freeze discharge seen in animals. Rather, they will frequently relate that they felt as if they were in shock. This is often related as a sense of detachment, numbing, and even confusion. Time often seems to stand still. Some patients report that they feel as if they are detached and removed from their body, occasionally reporting the events of the trauma as if they were seeing them as a third person. The out-of-body experience. Although some will relate that they were full of adrenaline, many report the sensation as one of remarkable calm. Although serious injuries may have occurred, pain is usually not intense during this period. A state consistent with the role of endorphins in the freeze response. Psychologists commonly refer to these phenomena as dissociation, which is defined as an unconscious process by which a group of mental processes is separated from the rest of the thinking process, resulting in an independent functioning of these processes and a loss of the usual relationships, for example, a separation of affect from cognition. Many researchers now feel that dissociation constitutes a major element of the freeze response, and people who report symptoms of shock and numbness after a traumatic event and exhibit symptoms of dissociation are actually in the freeze response at the time. In fact, many of the post-traumatic symptoms that occur often for years after the unresolved trauma are characteristic for dissociation, or the recurrence of the feelings and perceptions of freezing. When cues in the environment mimic those messages related to old severe trauma, the conditioned emergence of a failed act of self-defense may seem quite inappropriate and has been called conversion hysteria by mental health professionals. We will discuss this in detail in the chapter on dissociation. The salient point here is that human beings, at least in Western cultures, seldom go through the somatic and autonomic discharge after a traumatic event. One is tempted to consider the rarity of this phenomenon in human as a positive adaptation to basic animal behavior as a result of the brain's evolving frontal neocortex, which allows us to think, problem solve, and plan without the tyranny of primitive instinct. There is a real concern, however, that this apparent lack of physical completion of the traumatic experience in the human species may indeed not be a functionally adaptive mechanism. Instead, it may represent a dangerous suppression of instinctual reflex behavior, resulting in the imprinting of the traumatic experience in unconscious memory and arousal systems of the brain. An answer to this dilemma may lie in observation of animal behavior. Levine describes a conversation that he had with African gamekeepers. When they are captured, animals commonly enter a freeze or immobility response. After release, they will usually go through a form of reflex physical behavior typical of the freeze discharge. If they do not go through a period of shaking, however, the gamekeepers note that they will usually die after release into the wild. This fact might lead one to speculate that retaining the autonomic and procedural memories of the traumatic experience by these animals reduces their capacity to adapt to the threats and demands of existence in the wild. Basically, the freeze discharge may be a means of reversing, extinguishing fear conditioning, the prerequisite for trauma, PTSD. Clearly, self-protective skills in animals are likely to be inhibited if they are prone to experience states analogous to intermittent dissociation in humans, or if they are fear-conditioned. In fact, evidence indicates that freeze discharge may also be inhibited in animals chronically maintained in captivity, such as domesticated and laboratory animals, as well as those imprisoned in zoos and circuses. Indeed, early studies of the stress response in laboratory animals were limited by the intrinsic arousal associated with handling them, leading to the freeze response and subsequent experimental neurosis. In fact, the necessity for laboratory and zoo animals to live in cages may intrinsically create learned helplessness and subsequent vulnerability to trauma. Acculturation of the human species has resulted in an increasing pattern of urban living in closely confined habitats that intrinsically might inhibit the instinctual capability to flee or defend oneself under threat. This inhibition, in turn, might generate a state of helplessness, predisposing to the freeze response in humans under threat. The state of intense proximity and cultural interdependence may also act to inhibit the natural discharge of autonomic freeze energy in acculturated humans. The constraints and restrictions imposed on the populace of a complex culture by its institutions for the purpose of maintaining order may also intrinsically create a low-level state of helplessness. The suppression of the freeze discharge in humans may suggest that we also live in a cage, in our case a cultural cage. It may explain the prevalence of symptoms of trauma in complex modern cultures. If we do not discharge or complete the freeze response, our brains will literally be fooled by environmental cues into thinking that the memories of the traumatic event that inevitably periodically re-emerge represent events that are actually in the present and not actually in the past. When they emerge, we go through all of the experiences of that event, emotional, cognitive, and autonomic, as if it was actually happening again. Retention in procedural memory of this experience may serve as an internal cue for recurrent arousal patterns, alternating with numbing and dissociation, constituting the basically bipolar and self-perpetuating nature of PTSD, until that act of flight or self-defense and is unable to relegate it to memory as a past experience. And emergence of that past memory in present consciousness is likely to trigger repeatedly the freeze dissociation response. Conclusion. The theory that human trauma has its roots in inhibition of the freeze discharge after surviving a mortal threat has important implications for treatment of physical and emotional disorders in victims of trauma. The neurophysiological and neurohormonal events involved in the fight-flight-freeze response clearly have profound effects on all organ systems of the body. The truncated freeze discharge appears to be the physiological event that initiates the central nervous system changes leading to post-traumatic stress disorder. I believe that the effects of the unresolved freeze response on the body and brain have important implications for concepts and treatment of human disease. Many of those chronic diseases that seem to be the most common and which the field of allopathic medicine has been most ineffective in treating may well have their roots in the insidious systemic effects of cumulative life trauma. In fact, I believe that the most common complaint in current medical practice, that of persistent and unexplained chronic pain, has its roots in the actual changes in brain circuitry associated with unresolved trauma. As we have noted, the patterns of defensive and protective movement at the time of a traumatic event are stored in procedural memory for the purpose of adaptation to future related threat. By the same token, the pain and other types of sensory messages associated with the same threat are also stored in conditioned procedural memory, leading to perpetuation of the pain experience as a dysfunctional survival tool. As noted earlier, the bulk of my experience in human trauma is in MVA-related injuries, and the majority of these patients have the diagnosis of whiplash. The beauty of using the whiplash syndrome as a model for trauma is the fact that patients who have experienced this injury routinely present with a startlingly similar cluster of symptoms, many of which defy logical medical explanation. However, all of these varied symptoms involving many body systems are remarkably and logically explainable when viewed from the model of an aborted freeze discharge. And its neurophysiological and behavioral implications in the absence of tangible physical injury. Whiplash and its associated symptom complex represent a uniquely graphic depiction of the somatic consequences of trauma when viewed as a phenomenon of false procedural memory. The stereotyped and consistent replication of the sensory messages of motor responses of the body experienced in an accident are the primary symptoms of whiplash. Whiplash victims also have symptoms across the spectrum of experience: chronic somatic pain, cognitive, emotional, and neurological disability. In the face of an absent discharge, completion, extinction of these procedural memories, they will continue to emerge with any clue of the experience, involving the entire range of body sensations and motor defensive reflexes associated with the motor vehicle accident. Whiplash, as we shall see, is primarily based on trauma and procedural memory, and not primarily a physical injury.